Good morning, students. So I'm going to deal with the last topic of multi-degree freedom vibration system, and this method is very popular and is known as matrix iteration method. This is again a part of exact analysis for multi-degree freedom vibration system. So what we are going to deal in this topic, we'll discuss about the governing equation of motion, and then we'll discuss how to use this method step by step through an example problem. So again, there is a n degree of freedom vibration system. We have in our past lectures discussed about the governing equation in the matrix form in terms of flexibility matrix. Flexibility matrix A is nothing but it is 1 by K matrix. So you can write the governing equation of motion in terms of flexibility matrix like this, where flexibility matrix can be written in the form of influence coefficients. And in the past lecture, the previous lecture, we have discussed how to calculate different influence coefficients for multi-degree freedom vibration system. Now in this equation, governing equation, I put the solution, assume the solution X matrix is equal to displacement matrix sine omega t. Since we require value of X double dot, so we double differentiate this. So we get this as minus omega square X matrix sine omega t. We put the value of X double dot and X in the equation number 1. So the equation comes out to be like this. Sine omega t cancels out, and you rearrange this equation as X is equal to omega square A flexibility matrix into mass matrix into displacement matrix. Now this multiplication of A matrix, that is flexibility matrix and mass matrix, can be renamed by another matrix which is called as matrix B, which is nothing but some multiplication of the two matrices. So finally, the governing equation converts into the form of X, which is the displacement, is equal to omega square times of B. B can be broken down into elements of the matrix, and again X displacement matrix. Now how to calculate the value of, the purpose here is to calculate the natural frequency and the mode shapes at different natural frequency. Previously, I have told you that this method is being popularly used for calculating the natural frequency and the mode shape simultaneously, or more oftenly, the lowest natural frequency and mode shapes can be immediately calculated simultaneously. So in the next slide, I am going to discuss, taking an example, how to use this method for calculating lowest natural frequency and mode shapes. So here 3 degree of freedom system we have used. We have calculated the flexibility matrix for this 3 degree of freedom system. If you have any problem in calculating flexibility matrix for this, please refer my previous lecture where I explained how to calculate the coefficients, influence coefficients of flexibility matrix. So once you have calculated flexibility matrix, the mass matrix is in the form of 4m00, first mass, second mass 02m0, and the third mass 00m. By multiplying these two matrices, you will get the new matrix B. Now putting the value of B in the governing equation, you take out few common terms as m and 3k, so the remaining elements of the B matrix Now, to start the solution, what we need to do, since it is an iterative method, what we have to do is that you have to initially take the mode shapes by assuming x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3. So put these values of x1, x2, x3 here and on the right hand side. Now you multiply these two, you get this value of 11, 32, 41. Now you have to take this 11 common so that you can convert this in this form. So that is equal to 1, 2.9, since 11 multiplied by 2.9 is 32, and similarly 3.7. Now here you find that the mode shape where was assumed initially does not matches with the mode shape actually coming. Here it is 2, here it is coming 2.9. Here it is 3, it is coming 3.7. So we'll have to go for the next attempt, next iteration. So in the next iteration, the new values of x1, x2, x3 have to be taken as these values coming in the first iteration. So to start with the second iteration, you take 1, 2.9, 3.7 as the value of x1, x2, and x3. Multiply these two and get 14.1 common, you get the new values of x1, x2, x3. Here also, if you match it, x1 matches, but 2.9 does not match with 3.15, 3.7 does not match with 3.98. So you'll have to go for the next iteration. And in the next iteration, you'll have to use new values of x1, x2, and x3 as 1, 3.15, and 3.98. So with this next iteration, you go with this here by using the new values of x1, x2, x3 and multiply these two matrices, taking the highest, the 14.28 common, the remaining part in the matrix would be 1, 3.16, and 4. Now you try to match the value of x1 with x1, x2 with x2, and x3 with x3, which are approximately matching, means they are very close to each other. So it means that we have the values x1 is equal to 1, x2 is equal to 3.15, and x3 is equal to 3.98 represents the mode shape at this natural frequency. So this represents the natural frequency. How to calculate, you have calculated the mode shape, how to calculate the natural frequency. So you assuming that since this is equal to this, so this value should be equal to 1. Okay, that's how this value is going to be equal to this. Left hand side is going to be equal to right hand side if this value becomes equal to 1. So taking this is equal to 1, you can calculate the value of omega 1, that comes out to be 0.458 square root of k by m. Okay, so this is the lowest frequency which you have calculated, and you are corresponding to this frequency, natural frequency, you have calculated the mode shape as 1, 3.16, and 4. Similarly, you will have to go with the other mode, assuming other values like starting from 1, 2, and 3 for x2, x1, and x3, you can calculate other values of natural frequency and mode shape. So this method is called as matrix iteration method, which is being used for calculating lowest natural frequency along with the mode shape corresponding to that natural frequency. So students, in the last 4 lectures, what we have discussed is we have discussed various methods, exact analysis methods for solving multi-degree freedom system like matrix method, influence coefficient method, and matrix iteration method. Using matrix iteration method, both natural frequency and mode shapes can be calculated simultaneously. So we have dealt with multi-degree freedom vibration system. by using exact analysis. Now in the next lecture, I'm going to come up with more lectures on multi-degree freedom system by using numerical methods. Okay, friends, then bye for now. I'll come up with uh, new lectures on numerical methods for solving multi-degree freedom system. Thank you.